All right, welcome to the first session of today. If you are looking on how to focus more on your Java coding and less on the underlying infrastructure, this session is for you. So we will today cover how to run Spring apps in a serverless fashion. My name is Kieselhorst. I work for Amazon Web Services. We are both solutions architects taking care of guiding customers through their journey to the cloud. We have a lot of Java experience previously as a developer, so that's why it's a topic for us, and we are trying to improve your experience as a Java stakeholder on AWS. We are, as AWS, heavily invested into Java. We also have a booth upstairs. You can meet, for example, Volker, an OpenJDK committer who works for us there as well. So feel free to stop by. Now, Max will kick it off, and I will be back for the second half of the session.
Good. Yeah, so thank you, Dennis, and welcome everyone. My name is Maximilian Schellhorn. I'm a senior solutions architect with AWS, and I want to talk with you today about serverless Java with Spring. So whenever we talk about serverless in the community, we get a lot of different interpretations of the term itself, right? So serverless. For some, it's scale to zero, so compute that scales to zero, or for others, it's just function as a service. But at its core, serverless is a way to build and run applications without having to manage infrastructure. So full disclosure to start with, in serverless, there are still hundreds of thousands of servers involved. So this is Dylan from our infrastructure delivery team. So you don't need to deal with the servers, but Dylan still has quite some work to do. Now, in a sense, we're therefore shifting the responsibility of who deals with the servers from ourselves to someone else. And I want to take you a bit on a journey to see why we would want to do that in the first place, so in which circumstances and how we can do it. And most importantly, how can we adapt our Spring applications to act most effectively in those cases. So let's start with a server-based setup that we're all familiar with that deals with containers. So in a traditional container-based environments, we usually have a couple of components involved and we have full control over them. So we set up networking where we have an application load balancer, for example, a NAT gateway to talk from a private IP range to the public internet. And then we have our compute instances where eventually our applications will be deployed on. So what we do is we initially write a pod definition for Kubernetes or a task if we're using services like Elastic Container Services, where we define the container image and memory and CPU that our workload requires. And then the container orchestrator essentially runs this pod or our application, the container, on that existing compute infrastructure that we provided. Now, as load increases, we need to run more instances of that pod up until our compute instance is fully utilized, or at least a threshold that we defined in advance. And what then happens, we rely on tooling such as cluster autoscaling or Carpenter in the Kubernetes ecosystem to spin up additional compute instances so that we are able to accommodate the additional pods that we require. And one important aspect I think that we all take for guaranteed is that we're scaling here based on thresholds. So usually we scale a container based on 70 or 80% of utilization, and then we already spin up a new one to be able to ensure that we can handle a sudden traffic spike. And the same is true for the instances. So usually they're not 100% utilized until we spin up the second node, but usually we define a certain threshold to be able to do that. Now, in this environment where we have full control over all the components, the networking, the scaling, and the underlying nodes, we not also want to scale our workloads, but also our teams and infrastructure. So there's this whole trend of platform engineering evolving where we build abstractions over all the complexity that we are dealing with to then provide things like self-service to our developers, or also deploy not only workloads, but infrastructure components. So you can run databases in your Kubernetes cluster via operators or messaging queues and so on and so forth. All that is to say that in those environments, we have the full flexibility on what we do, but we also have the full responsibility about all these components. So maybe serverless can already help here to simplify a bit of that. Because on the compute instances, we also are responsible for patching them, maintaining them, draining the nodes when we do cluster upgrades and things like that. So there's quite some responsibility involved as well. And here we can see a notion of how serverless can already help. So instead, this is just an example with Fargate, but you can pick any other container service that you prefer. But there are usually always the concept of that you do not need to manage the underlying nodes anymore. So this is AWS Fargate, our serverless compute service, which essentially runs your containers in isolated single-tenant environments, and they're isolated here on a virtualization boundary. So there's no sense of an instance that you need to put in advance, like a dedicated VM. You just define CPU memory, and then it will be run somewhere, but it's not, you're not responsible of maintaining the underlying VM and so on and so forth. And I think you can see this broad spectrum in the ecosystem quite a lot, right? So you have the option where you can have the full responsibility, deal with the networking, the scaling, the actual compute nodes. And then there are always different abstractions to reduce some of that responsibility up until the point where you don't even need networking anymore, where you just drop the container image, you get a public endpoint and you can invoke it, right? So depending on the level of abstraction, your responsibility changes. Now you might ask yourself, okay, we have containers, we have serverless containers, we are done, right? We don't need anything else. So why not just build anything from containers? Maybe containers are the answer to every compute architecture decision that we want to make. But today we want to also cover a bit around functions. But why would we need functions in that sense? And there are two main things that I want to highlight from the containers that we take for guaranteed, where maybe a functional model could even help us further. And the first one is that we still have the coarse granularity of scaling when we talk for containers. So in containers, usually we deal with a certain bucket. So one container can, for example, handle 100 requests at a time at maximum. But even if we just get 3 or 4 requests, we still have the entire container provisioned. And as we said, when we scale up a new node, we are not 100% utilized. So usually we always have a larger bucket than we actually need for the handling of the actual requests. So this is one. So maybe we can scale a bit more fine granular, maybe even on a request level. And the second is the long-running nature. So containers usually expose a certain set of functionality on a given port, like port 80, 443, whatever. But so usually they keep on running. They might be polling from a Kafka stream or from a queue. So usually containers are more of the long-running nature. And even if you can spin up containers on demand, usually there's still some cluster component that takes care of that additional scale up, right? So you have the cluster itself that is running, there's an operator. So even if you use things like KDA or Knative to have event-driven containers, usually you have still the cluster then running at least somewhere, or the billing is at least more coarse granular because you need to pay for a certain amount of time. So maybe here in that case, functions can help. So what is a function? A quick introduction of who has not dealt with functions before. So a function is essentially, you can think of just as another Java method that you usually write. And there's like one specific aspect of it. The function, depending on from where it gets invoked, we will cover that a bit later, essentially gets a different input argument. So if it's invoked from an API, it gets a different input than when it reads from a queue, for example. And then we have a context object, and in the context object, we have additional information such as unique requests ID or something. But that's it. Just think about it as a normal Java method that you would write. And then when you hand it over to a function as a service, you essentially then just define very basic configuration, the memory that you need. The CPU is allocated proportionally in case of AWS Lambda. You put the runtime version, and maybe the CPU architecture, x86 or ARM, and that's it. So if we look under the hood how that works and how it is different in contrast to containers, I prepared here a very simple function that reacts on an API request. So this is, as you can see, just a normal Java method. So we have a class, we have our logger, and here we have this handle request method. And the handle request method, for now, we just take a map of string object because we're not so sure about what we're receiving here, and we get the context. So we just get from the context the ID, we log it, and then return a response. So this is a very basic function you can write without any framework, essentially. Now, as containers need to run on a compute node, the functions under the hood, as we said, they also need to run somewhere. And this is usually on a Firecracker micro VM that under the hood runs on bare metal EC2 instances. Okay? But the most important aspect is that you do not have control, that you do not place your function on that specific instances and expose a certain port or something. You usually only talk to the service directly, and the service makes sure to basically then put your function on that bare metal EC2 instances under the hood. And this is a very powerful concept because that allows us to scale to 0. So even if there's no request coming in, and let's say the first request comes, it hits the service first, and then it spins up the functions on the underlying bare metal EC2 instances. And this is very much different because you're not, as I said, exposing here an HTTP port on a given port, right? Your function gets invoked actually at a predefined entry method, which is called the Lambda function handler, for example, right? So you basically just, the function that I explained before, you bundle it as a jar, you hand it over. Now the service needs to understand which method to call when it spins up your function. So this is where you put the Lambda function handler, which will be very important also later. Now, not only does it allow scale to 0, but also rapid scaling, because we have the service that knows how many requests coming in. It can automatically scale based on the number of requests. It can spin up additional function instances. And this is also handy when we think about event-driven workloads. So here you see a function that handles items from a queue. And this is, again, usually we have the mental model that when we build an application that pulls that reads from a Kafka stream or pulls from a queue, we have a client library, right, that at a certain interval pulls and see if there are messages. But here the model actually changes. It's not the Lambda function actually pulling from the queue, but here again, it's the service that does it for you via a concept called event source mapping. So what does it mean for you as a developer? It means that you already get, as an input argument to your method, you already get the messages that has been read from the Kafka topic or from the queue. So you do not need to implement a client library that pulls. You already get that as an input argument. So you see here we can do SQS, get records, stream, and then basically deal with our messages already. And this is a fundamental shift on how we would build it in a container. Right here, functionally users usually get invoked, while containers usually keep on running and constantly pull from somewhere. And again, the entry point here will be invoked on that specific method, and my additional arguments will be passed. Now, before going into the Spring specifics, I want to here spend again a moment on how these input arguments look like. So you see here an HTTP request that hits an API gateway, but what the Lambda function receives, as I said, since we're not exposing this HTTP component, we are actually getting a JSON representation of an HTTP request as this input argument, okay? The same is true for Kafka. So we're not getting a plain Kafka record, but we get a JSON representation that basically has all these components. And AWS provides open source event libraries so that you can have a POJO that basically maps this structure already. But if you would do that, then you basically tie your application code to AWS specifics, right? You would have Amazon API gateway, POJOs all over the place, but maybe you do not want to do that. Maybe you want to deploy your function also to different providers. And here, the beauty of Spring Cloud Function comes in. So I'm not sure, has anyone ever used Spring Cloud Function before? Okay, 2 folks. Good, so then I will spend a brief moment here. So what Spring Cloud Function does, it promotes the implementation of business logic via Java functions. And the core idea is that it provides a vendor agnostic way so that you can write a function on any basically cloud provider without needing to change your code. And in the context of Spring, a simple functional application is just an application that has one bean of type, at least a function, supplier, or consumer. So that's it. So that would be a full functional application. Okay. Now the advantages, I already teased them a little bit. The advantages of that is that you, first of all, can leverage all the things that you're used to in the Spring ecosystem. So you can use dependency injection, Spring Data for talking to the relational databases, and also your common testing methods, right? So from that, the programming model essentially doesn't change. And it provides here this context-agnostic input argument. So you see you have a message wrapper. There is nothing AWS specific here on this function on the left side. And this is the core idea. And how does it work under the hood? Spring provides a class which is called function invoker, which has all the AWS specific internals implemented in the library so that you not need to deal with that. So let's say this request comes that we explained before, which is an Amazon specific thing, an API gateway request. But what the function invoker will do, it extracts the relevant body part and makes it a business pojo for you here in the function. So you see everything is abstracted, essentially. Now, the function invoker, as we said, we have here this specific bean. So for example, handle pet delete function. This is the only functional bean, let's assume, in our application. So for the function invoker, it's quite easy to know which specific function to invoke. But we actually might have multiple functions. We do not want to just have a handle pet delete function, but also a handle post pet function. And here we need to be smart. We need some additional routing information to tell the function invoker, okay, which functional bean should you invoke, right? Because it registers multiple functions. Where should it know from which function to invoke? So you need to provide additional routing information, okay? And this routing information can be provided in two ways, either via application properties. You're probably all familiar. You could say Spring Cloud function definition and then say handle pet post function, and then it knows when it starts up, okay, this is my primary bean, so to say, that I want to use. As you know, you can provide Spring-specific configuration also via environment variables, right? You usually do that with things like the JDBC URL or something like that. So you could also provide that as an environment variable, which function to choose. But you can also leverage more dynamic ways of achieving this. But it depends here a bit on which deployment model you choose. And I will share some insights here on what are the options. So the first option that I mentioned, so defining it statically via an environment variable, for example, makes sense if you want to, you have a single Spring Cloud function project with two functional beans, but you want to deploy it to two separate Lambda functions, for example. So why would you want to do that? The use cases for this is that if your functions have completely different permission sets, so let's say one function talks to a DynamoDB, the other function talks to S3, then usually the Lambda function itself requires different permission to access this resource or the other. In that sense, it makes sense to have two separate Lambda functions so that every single function can only do the things that is allowed to do. The second one is if you have completely different scaling patterns. So let's say you have one function which gets hammered with 100 requests per second and the other one is just invoked twice a day. It would also make sense to define maybe different scaling mechanisms or different thresholds for that. So whenever you require a different set of permissions or requirements per function, maybe even different memory settings, it makes sense to deploy them as two separate functions. Now, as we said, we want to use the function invoker. So the entry point for both functions will always be the same. We always use the function invoker. And now we need to then tell Spring, okay, if you invoke this function, please call this method. And here we can just provide a different environment variable so that it knows where to go. So we can do that at deployment time. It's static, you cannot change it. Whenever you want to change it, you would need to deploy a new function. So it's not a dynamic approach, okay? Now, if you would do that, you might ask yourself, and we get that questions quite a lot when folks coming also from the container space. Okay, if I create a function for every CRUD operation, will I not have hundreds of functions? So I've seen projects where folks had like 2 REST API endpoints /unicorn/orders and every 4, let's say, HTTP methods. And then they created 8 Lambda functions out of that, for example. Okay, there are use cases when you can do this. I will talk about that a bit later. But usually this is not the only mental model that you should have, because you can also deploy the same or multiple Spring functions, functional beans, into the same Lambda functions. And this makes a lot of sense. So that it would look like this. So we deploy the whole code to just one function, but then we need a dynamic approach based on a request to decide which functional bean we would want to do. So we not do it at build or deployment time via application properties, but dynamically during runtime. And this makes a lot of sense if you are doing a CRUD operation. For example, on /orders, you most of the time want to have create, read, update, delete in the same code repository. First of all, you're dealing with the very same entities usually. So if you would split everything out, you will need to think about how do I share the entity classes between them, all that kind of stuff. And there's an additional benefit for less cold start. So Dennis will elaborate a bit more later on how that works. But essentially, if you first do a create pad and then a read pad, under the hood, it might hit the very same Lambda execution environment, and therefore you do not experience as many cold starts. Okay, Dennis will elaborate on that more. And it's a simpler deployment model, right? I have CRUD operations on that, and I just deploy a single function. It also simplifies the deployment. But when we do that, we now need to define dynamically which function we want to call. So you see here, let's say we have 3 functions, post, get, delete, and we get here our requests from function invoker. And one option to handle this is now use the HTTP header to decide which function should be called. So you can provide Spring Cloud function definition also as an HTTP header. And if we do that, we can then call this function. And then if we get another HTTP header, we essentially route it to different functions here. So it's really dynamically per request. Now doing this, you have an HTTP header. So sometimes there are situations where you do not want to do this, because if your client is able to set this header, the client itself could decide on which function to route, and you probably do not want your users to be able to decide that. So therefore, there are custom logic that you can implement, message routing callback, that you just need to register, where you can define your own dynamic routing mechanism based on a request. So let's say you get the request, the callback will be called. You then decide, based on the event that you get, which function should be called from the function invoker. So this is a much more dynamic approach, and usually recommended in more advanced use cases. Good, so let's recap what we have learned around this function. So when would you use this functional approach? You would use this, first of all, it's the best practice to use that for messaging-based application. When you deal with Kafka, RabbitMQ, or SQS, you would use this functional approach where you provide the handler and then you do something specifically on that. This functional approach is also good for small to medium-sized APIs. So that means if I have 4 CRUD methods, it makes a lot of sense to have those 4 functional beans, and then with a dynamic routing approach, decide on where to route. As you know, if you rely on a traditional Spring Boot web application, there is usually an embedded Tomcat server, right, that exposes the HTTP functionality somewhere. With the functional approach, you do not need that anymore. So therefore, the applications also tend to start up faster. And last but not least, you get this great portability and testing experience. So there is a module also in Spring Cloud Function called Spring Cloud Function Web, which allows you to locally test the functions by exposing it at HTTP endpoints, and you can rely on traditional Spring integration testing. But the most important takeaway is that one Lambda function doesn't necessarily have to be a single Spring Cloud function, and choose that based on your deployment module. Now you might ask yourself a little bit, okay, now I have already maybe my Spring Boot application with /unicorns. I have this nice REST controller, and now I need to rewrite everything on a single functional beans. I mean, that seems like a bit of an effort. Can I just not use the traditional REST controllers that I'm used to? And Dennis will share a few methods on how to deal with that.
Thanks, Max. Yeah, right. So Java turned 30 this year, right? Spring is around for 20 years. So you may have wondered with all the new codes and classes, and not a lot of you have already explored Spring Cloud Function, what to do with the existing code, right? Do we want to rewrite it? Of course not. We want to reuse it. And how do we do it? We do it similar to our US colleagues who came here to speak in other sessions and try to plug in their American socket into the European standard. It doesn't work, so they use an adapter and plug it in between. And that's the same that we do here. So we use an adapter that translates it for us, so we can easily re-platform our existing Spring Boot application to the world that Max just showed without rewriting it to the new patterns. So we insert the adapter, and what the adapter basically does is it translates the JSON objects that we've seen, like the API gateway request, to the Java servlet specification requests that all the frameworks that we have, including Spring, understands. And that basically means there's no need to rewrite anything on our end. We just plug it in and it works. And what we did at AWS to make it work, we created a project that is called AWS Serverless Java Container, which basically does the transformation handling of all the AWS specific API gateway requests and other things that come in to the Servlet API specification. And the newest version of that, I just released it yesterday, supports the latest Spring Boot version, 3.4.2. And it also supports Jersey, should you be looking for other frameworks. But this is like what the majority is using. How it works is you just add it to the project, and later on we also see, should you be willing to use GraalVM, for example, this is also supported. The basic difference between the traditional servlet container that we have here on the left-hand side is usually in your Spring Boot app, you have bundled embedded Tomcat, right? And the Tomcat exposes the port, like 8080 by default, and allows the application to receive requests. And on the end, there is also the HTTP servlet functionality underlying in Tomcat, capsulated obviously by Spring Boot. So you just have your REST controller, but this is what happens under the hood. What we are doing with the adapter on the right-hand side is we take out the Tomcat server. We no longer need it because your Java runtime environment, there is no port exposed to the outside world. It's event-based, as Max was describing it. So there is no port exposed. We can drop the whole Tomcat from our deployment package, right? We just get the events. But obviously, Spring expects the requests. So that's where the translation happens inside the library, so that it still seems like it would be a traditional servlet request. If we zoom in a bit into the Spring specifics, within the last years, we also collaborate with the Spring team to unify it a bit more. When the project initially was created, we had like our own request chain where the whole thing flew through. But nowadays, we even co-engineered the part that does the translation. So this project also uses Spring Cloud Function under the hood. So the request handling is done by Spring Cloud Function, and then in the end, it's chained through Spring Web, Spring Boot, and the Spring Framework as it used to be. Again, a manual, and also if you follow the QR code, the slides will be obviously available later on as well. You just add the library to your Maven or your Gradle project. Then you configure a handler class similar to the function invoker that you have just seen. There is a Spring delegating Lambda container handler. So you don't need to write one on your own. You can just use this. And this will delegate back to your Spring application class of your existing Spring Boot application. You can even configure it using an environment variable. Then you change the deployment a bit, which means the packaging needs to be different compared to how it was done before. You upload it to Lambda as a service, and then you can run it. And that's it. So no additional code or any rewrite of your existing app required. The advantage is obviously you can just keep the controller style that you've been using for multiple years. No need to rewrite it, and you can easily port your existing application. And compared to how we've seen it with function, it's obviously a little overhead because of the transformation logic, right? It's less native than writing a new function from scratch. But still, I think for HTTP workloads, it's the ideal way to go. It works very well. Whereas the approach that you've seen from Max is if you have like message queuing or Kafka, where you want to process it directly from there, that would be the way to go. Or obviously, if you write new functionality, you can explore to write it in a Spring Cloud Function way directly. I think another benefit is also the portability. Should you be noticing like you want to move back your code to something else, right? Out of the function again to a container, for example, because you notice like from the scaling perspective, a container makes more sense. Then it's easy, right? You just take out the Spring Boot app again and you put it back into a container or somewhere else. Good. A key aspect, and we already heard about cold start earlier, is performance. So why do we need to watch out for performance? First, we need to understand the execution model a bit better. We already heard it scales to 0. So how does it work if the Lambda service handles a request? So first the request comes in, obviously, and if we scale to 0, obviously there's nothing running that can handle my request. So the first thing is the service checks, is there an execution environment that can serve my request? If it's the first one, obviously the answer is no. There's no execution environment. So what happens is an execution environment gets created. That means a micro VM is started. And inside the micro VM, obviously, the code needs to be downloaded. So you provided your jar file somewhere. The jar file gets loaded. The runtime, which means the JVM, is started. All the classes need to be loaded. Everything needs to be made ready to serve your request, and then the code can get executed. And if you think about yourself, how long your Spring Boot app takes to run until it can serve requests, a lot of performance optimizations have been made with the newer Spring Boot version, but still, it takes a few seconds, right? And if you add the speed that you have, or like the duration that you have from JVM and class loading and all the other stuff, you can easily end up with 10 seconds, 15 seconds, something like that, depending on how much dependencies you have bundled into your application. And now think about your user that did the HTTP request, waiting for the response, and it may be that the website itself, you have multiple services that get called, so you don't want to let your user wait for 15 seconds until you can render the website for him. So that's what we obviously refer to as a cold start. The request afterwards, so once the execution environment is initialized, will be faster, obviously, right? So the execution environment stays warm for a certain amount of time. So if you do a second request afterwards, it will be super fast. But that doesn't help for the first request. Just to illustrate that a bit more, here's the first request coming in. Execution environment number 1 gets created, initialized, and executed. Now, if the second request comes in after the first request is already finished, we can reuse it. If in parallel a third request comes in while the execution environment is still busy with the second request, a new execution environment gets created and we need to run the initialization again, which means another cold start happens. But by doing so, we have a very good way of scaling, right? If there are a lot of parallel requests, the service takes care of scaling the stuff for us. Here's another force request. And if there are no requests, at some point, all the execution environment will be terminated again, and there are no costs. So that's the beauty for us. If I have, for example, an application where I have just a few requests per day, it's very cost efficient. But obviously, we still have this problem with the cold start that we need to deal with. And here's just an overview about the things that we can do. So on top, you see no optimization. And on the left-hand side, you see it's like 13 seconds for the sample app that we've been using. Can be more, can be less. Just the average app doing CRUD operations like the one we've seen. This is the one that takes 13 seconds. So not really good for us. If we kick out certain dependencies and do a bit of tweaking with JVM parameters and stuff, for example, there are very big logging frameworks. If we go to a simple logging for J, for example, and use smaller libraries, like instead of Hibernate, we just do JDBC and this kind of stuff, we can get it down to 6 seconds, maybe. Or even if we use no framework at all, we may be down to 2 seconds. But yeah, we have a lot of frameworks, right? Our apps use frameworks. We use library. We don't want to write all of the code on our own. So what do we do? Here we have, you see it at the bottom, 2 most promising features. The first one is SnapStart that I will be covering, and afterwards we also take a look of how to combine it with GraalVM. So SnapStart is a functionality that we launched to especially address the cold start without the need to artificially keep the environments warm, for example. Some customers also built like ping functionalities where they artificially said like, yeah, I do a request for monitoring every few times so the environment is warm. I said, wait a moment, does it sound right? You want to have it scaled to 0, right? To be cost efficient and not wasting resources while there is no requests. So you don't want to do it. What SnapStart does, it's a managed functionality to help you speeding it up. It takes a snapshot of the whole execution environment that you've just seen. So the initialized execution environment where all the classes are ideally loaded into memory already, and the environment is ready to execution, we snapshot it. That's a Firecracker micro-VM technology. If you want to dive deeper, there's also a paper and stuff around that on GitHub. But basically, we take the whole thing, it's initialized, and once your request arrives, we restore that initialized environment. And that's a magic on how we speed it up. So it lives in a low latency cache, and that's why we can make it available very fast. So the similar diagram again. And here we show you how it's different. So to take the snapshot of the initialized environment, obviously when we are deploying it, we need to initialize it once to take the snapshot. So that's why the deployment takes a little longer, because we already create an execution environment there, we run it, and we create the snapshot and put it to the cache. And once the request arrives, we resume from that snapshot. Everything is loaded already. We can just run your code and execute it. And the benefit in the end is obviously minimal code changes. I get back to that on the next slide. But you can gain advantages of 80% for the cold start time, which means depending on what application we use. Here we use the one where we already made some optimization. So we had 7 seconds before, and we got it down to 1 second. So what may be things to watch out for? So if we take a snapshot of an initialized JVM, obviously, and imagine it talks to a database. So I establish a database connection, for example. If we have the relational database, I have the JDBC connection initialized on startup. Once I resume from the snapshot, the database, obviously, on the other end, it will have killed my connections already, right? So the snapshot was taken at deployment time, and when I resume from that snapshot, the connection is invalid. And there may be other things that I want to take care of before taking the snapshot or after I resume from the snapshot. And that's where we can use the CRAC interface. So CRAC is coordinated restore at checkpoint. It's a different functionality. There are own sessions around that. To be clear, we are using that interface, but not the underlying functionality because we snapshot the whole execution environment, not just the JVM. And CRAC itself is a technology that's just taking care of the JVM. We snapshot the whole environment, but you can still use that API. It has two methods, before checkpoint and after restore. And by doing so, you can, for example, in before checkpoint, you could close the database, and in after restore, you could re-establish the connection. And other things may be dependency injection, for example, or you want to take care to look into loading specific classes before the snapshot has been taken. That's all that you can influence using that interface. With regards to Spring, because we're dealing a lot with Spring apps, it's very beneficial that in Spring Framework 6.1, which is bundled since Spring Boot 3.2, you already have those CRAC interface implemented. For example, if you are using the integrated functionality using Hikari connection pool, there is already a functionality inside Spring that takes care of it. So you can just enable it, add the CRAC library to your project, then the CRAC delegate inside Spring will take care of it automatically. That's very, very convenient. So you can also benefit from that feature. Good, the last thing is GraalVM. So who has heard of GraalVM already? Yeah, it's getting well known already. So GraalVM is in the end, if you want to get the most out of your Java application, you can move to GraalVM. For those who've not raised your hand, it's a different way of running your application and also includes a different build and deployment lifecycle, right? In the end, when you execute your Java app, it's no longer running on a JVM. And this is what we call in terms of Lambda a custom runtime. So usually we provide you with a managed runtime by us. So you get, for example, JDK 21. And if there's a JDK update or a critical patch or something like that, we as a cloud provider, we take care of it, right? You get the new JVM version inside your Lambda service that you can just use, no need to take care of updates or something like that. For GraalVM, there's nothing like that. So you basically provide a binary in the end. And for those of you who have already tried it, you know, like it takes a lot longer to build your application and to provide that end result of the build process to AWS Lambda, you need to bundle it in a custom runtime in the end. We also have it here. So here's basically the process. You bundle the output in a zip file and you provide it to the Lambda service in the end. The good thing is the startup is really fast, so no need to do this snapshotting functionality that you've just seen with SnapStart. The memory footprint is also lower, so that all sounds great. There's also support in Spring Boot nowadays, but there's some things to watch out for, right? It doesn't work with every library, obviously. Things like reflection won't work, so it's not as easy that we say, okay, use it for every application. This is the future for every Java app. Usually what our customers do is they first try what to get out with SnapStart. And if it's really low latency, milliseconds matters, then people try GraalVM. Good. That's it from the overview perspective. So you see here we have different ways of optimizing it. If you have your existing Java app and you think, okay, it was a bit fast for me, there is also a workshop available that we can obviously run with you and your company, but you can also run it on your own by just getting through the website. You can deploy a sample application and go through it in parallel. In one of the other rooms, my colleagues are also running one of the labs in this workshop with some attendees here, but this is also available for you to run later on. It's always good to just try things, see how it feels, and then later on transform it or transfer the knowledge that you gain to your own application. If you have some questions, we have 5 minutes left now. Before we start with it, I'd like to ask you to also fill out the survey. I really appreciate that the Jfokus folks have the survey functionality this year, so make sure to rate all the sessions that you've been visiting. And now, as said, thanks a lot. 5 minutes for questions. Who wants to go first?
No one.
Yes.
You have an example how the adapter works. So this would be like Node.js serverless, we have like a routing configuration file for which path execute which method. And this is very working in Java.
Yeah. So the question was, if we have an example on how the adapter works, how the routing works under the hood, which method goes to where. So basically what we do with Serverless Java container, we do not split it off, right? So we take the whole application that you have, and you have the path specified on your REST controllers. And we just, from an API gateway perspective, we do a star routing to that application, and the routing is still done the way you have configured it in your Spring app. So should you not be happy because you think, oh, the Spring Boot is already too big and I should ideally split it amongst the things that Max told you, you can obviously split it and refactor it into different services later on. But by default, it would be the same way on how the routing is configured in your existing app.
Yeah, I mean, how it's built is we have it on GitHub in the Serverless Java container project. You can actually see what it does. So it essentially takes that JSON payload from API Gateway, and then it builds an HTTP servlet requests, and then hands it to the Spring Framework, because that's what Spring Framework would need, right? So if you want to see how that mapping is done, it's open source in the GitHub repository.
When you say serverless Java container, is it still running the managed AWS Lambda function, or is it in a custom runtime?
It's in the name, to be honest, is not ideal. I think it comes from servlet container, but container is a bit not so long a good word. So it's still the managed runtime. So you still benefit from the managed updates and all the functionality around that. Other questions?
These Lambda functions are made not very ideal for the continuous high-load applications that they run on the containers. So in that case, I have actually two questions. How would the scaling can be monitored and configured? That is the first question. And the second is how the health would be monitored and how they ensure those functions are there.
Yeah, so the question was that there was an assumption that Lambda does not work well in like very high load scenario, or is not efficient. And the question was, the first question was, how can you monitor, or the second question was actually, how can you configure the scaling, and how can you monitor for any errors? So I mean, scaling itself, you have a different So first of all, if you do not apply any configuration, Lambda would scale up onto a count limit. So in certain regions, that's 1,000 concurrent execution environments. So you can limit that per function. You can set a reserved concurrency, for example. So if you have a database that can only deal with 50 concurrent requests, you probably do not want to throw 1,000 functions on it, right? So you can set like a maximum cap, and then the requests would get throttled. In those cases, usually what we recommend is using an SQS queue in between, and then you can define a maximum concurrent poller mechanism. So the messages get saved, so not rejected in the queue, and then you spin up a maximum of 50 concurrent pollers, which will then talk to your databases. So this is how you can influence the scaling mechanism, either cap it or decouple it via a queue in between and cap it on the queue consumers. Does that answer the first question? Okay. And the second question was around monitoring. So we provide out-of-the-box metrics via CloudWatch. So you would see the number of concurrent requests per Lambda functions, how often it is invoked. And then depending on the service that you're using, for example, API Gateway, you also get metrics on how many invocations resulted in a 400 error or a 500 error. So usually in the metrics tab in the Lambda console or in CloudWatch in general, you basically can, you see all these different metrics. And we have a lot of our partners, so things like Datadog, for example, they also provide mechanisms to monitor all those metrics related to the Lambda health. Make sense? Okay, good.
Good. I think one last question.
What if you have resources that need to access, if your function needs to access resources which are limited to a certain VNet, can you still utilize this plugin?
So the question was if a Lambda function needs to access resources in a dedicated network, for example. Yeah, so we have VPC-enabled Lambda functions. So if you have a virtual private cloud, so essentially our networking concept, where basically you have an RDS instance, or let's say any database in a private network, you can basically attach a network interface to the Lambda function. So you can have Lambda VPC-enabled functions, and then essentially your Lambda function has access to that IP range in that. So yes, you can invoke private resources via a Lambda function by using VPC-enabled functions. Okay.
All right. If there are more questions, we'll be around. As said, we also have the booth upstairs. Thanks a lot for joining.
Yeah.
And hope to see you soon.
Yeah. Have a great day.